So hello everyone. In the previous sessions, we have discussed some things about probability. We discussed the basics of probability. Now we'll shift our gears and we'll discuss what random variables are. I did not want to name them first. Let's see first why this concept is needed, because we'll motivate the concept first, and then after that we'll have a thorough discussion onto this. Why is it needed? Because we were discussing about the algorithm logistic regression, and I told you that there is a probabilistic interpretation in that. Okay, so for that we have to have a probability background, and that's the sole goal of having resuming these probability lectures. Now just some basics of what we have done so far. I'll revise a bit. So there are three axioms of probability. We discussed what probability is. It's some sort of uncertainty that we define, and then we said there is something called a sample space, all the possible outcomes, and there is an event. Whatever happened is called an event. There is an experiment. Whatever you do is called an experiment or a trial, maybe sometimes. Okay, so all these concepts I hope that you already know. I just wanted to name them so that we'll set the context and discuss about the random variables. So now you know that there is a probability function. Let's suppose we have a sample space. Okay, we have a sample space. So in the sample space, you know that there is all the possible outcomes are there. Okay, there are all the possible outcomes. Each of this is an event, singular event we call it. So let's suppose we are tossing two dice. So what is the sample space there? So sample space there is 1, 1. So on the first die, 1 can be there. On the second die, we'll see 1 also. So this is one of the element of the sample space. Then 1, 2 can be there, and so on till 6, 6. So these are all the possible outputs or all the possible outcomes that may happen when you roll two dice together, or when you roll a dice two times. Okay, so it can be two things. So you can roll two dice together, roll two dice together, or what you can do is you can roll a die, roll die 1 and then die 2. And both of these experiments are somewhat similar because they'll give the similar sample space. Okay, now what we said is, we said okay, we now assigned probability to each of these. So we assign some probability. So what I said is, because we have uncertainty, we don't know what will happen, and what we assume is we make some assumption, as we do not know everything about the experiment. So now we'll assign some probabilities to each of these. So we'll assign these probabilities to each element that is in the total sample space, or that is in the full outcomes. Okay, we assign some probability. Let's suppose if these are we consider them uniform, so we'll give all of these 1 by 36 probabilities that we have sent. That we call each of these outputs or each of these outcomes are equally likely. So if there are 36 outcomes possible, so each one of them will get 1 by 36 as the probability. Now let's think this problem as a different thing. Let's suppose I don't care what is there on the die. I care about something else. Okay, to motivate this problem, let's see like this. Let's suppose you are concerned with what if I throw a die twice? What's the probability that I'll get the sum of number will be 7? Sum of numbers on two dice will be 7. Sum of numbers is 7. Let's suppose you are concerned with this now. Okay. Initially, what you did an experiment. Now you are not concerned with the output that we are getting. Okay. As a whole, if you see there are possible outcomes now, but what you see is you are concerned with something else. Okay. So how can this happen? This can happen in different ways. So let's suppose 1, 6 can happen. This will be 7. 6, 1 can happen. This will be 7. 5, 2. Okay. 2, 5. And so on. Let's suppose 4, 3 and 3, 4, something like this. So now you're not concerned what happened on the die. Okay, whatever happened on the die, that happened. But what you are concerned is, you are saying that I want the outcome to be 7. That is, I want the sum of numbers on the two dice to be 7. Okay, that's now what you are sort of concerned with. So this can be like this. So again, to motivate the real world problem, this is one example where you are not concerned with the exact outcome, what happened on the two dice, but you are concerned with something else. Similarly, let's suppose you have some people. Okay, let's suppose you have 4 people, A, B, C, D. You can randomly pick one of the guys. Okay, let's suppose consider an experiment where you randomly choose one of these guys. So maybe these guys are in the room, and then you randomly go in the room with a blindfold on your eyes, and what you do is you just pick up a guy. Okay, maybe, and it may have some probability. Now you may not be concerned with this. Let's suppose what you are concerned with, whoever guy was selected, what is the weight of that guy. Okay, or what is the height of that guy. Let's suppose you are concerned with weight, or you are concerned with height, something like this. So now if somebody says me, okay, we selected A, so what you will do is you will say probably the weight was some 60 kgs or something. Okay, now you see this as a function. Again, the same thing can happen here. What is the height? Height can be, let's suppose, some in meters, some 1.6 meters. Or similarly, if you perform the experiment and then second time you selected the C. Okay, now if you see that weight was, let's suppose, some 65 or something, and maybe the C had more height, it was 1.75 meters. Now you're not concerned about what actually happened. What is the outcome? What you are concerned is something else. You are concerned with what was the weight that I chose. I chose a guy. He will have some weight. So what was the weight of that person? Or similarly, what was the height of that person? This is why we use random variables. So in random variables, we are not sort of concerned with what is the output of the experiment. But what we want to do is we want to know something, some property, if it happened or not. Okay, we'll see it how it's a function and some things like that. And similarly, we'll again go back to this example. Let's suppose coins. Example of coin. We'll take an example one. So example is, let's suppose we are tossing 3 coins. Okay, there's a three fair coins are there. So 3 fair coins are there. Now I'm tossing these coins. Okay. Now my question is, I'm not concerned about what is the actual output, what is the actual outcome of the experiment. So if I ask you a question, tell me the probability that that the number of heads is is 3. If I tell you this, okay. So now if you see that, I'm not concerned what happened on the output, or maybe let's suppose I'll take number of heads is 2 or something like this. So what this number of heads can take the value. So this can take the value 0, it can take the value of 1, it can take the value of 2, it can take the value of 3. Everybody with me? Everybody agrees on this? I made I told you, let's have a probability of this. So this statement over here, number of heads. So number of heads can be 0, it can be 1, it can be 2, it can be 3. Why? Because we tossed 3 coins. So all outputs for I'm not I'm not concerned about what will be the real outputs. But what I'm concerned is I want to basically count the number of heads. So sometimes I can tell you what's the probability of that number of heads appear is 3 or is 2 is 1. But you know that the total number of these things, this is the total possible outcomes for this thing. So for number of heads, I can either get 0, I can get 1, I can get 2, I can get 3. Okay, this over here is called a random variable. Okay, this is a random variable. Why is this random? Because again it takes random values. If you see it, by definition, why is it random? Because it can take any of these values, any of these 4 values, 0, 1, 2 or 3. So we named it as a random variable. Let's call it this x. This is a random variable x. Okay, so now how I can write this? Let's suppose I can write p of x is equal to 0. So this over here means that this random variable will take value 0. Now you know that random variable will take one of these values. Okay, so probability that x will take value 0 is equal to this. Probability that x will take value 1 is equal to something. Okay, we'll have to find these values. X is equal to 2 will take some values. This is a gentle introduction about what a random variable means. So random variable basically what it does is, so in here we are not concerned about what is the actual output. Now what we try to do is we try to somehow create a mapping which takes these events, maybe collection of events. It can take this collection of elementary outcomes and then map it to some probability. So here if you see, so we had these possibilities. We had head and head. Let me write it like this. Then head and tail, tail, something like this. So what we will do is, now you will map these to some numbers. You will map these to some numbers. Here we have, what are we counting? We are counting number of heads. So this will be mapped to, let me exactly like construct it. Okay, let me enumerate all of these. So how I will do it? So first will be head and head. So then probably I'll write head, tail, and tail. Head, tail. Okay, and these are all possible outcomes in the experiment, because the experiment was we are throwing these coins, we are flipping these coins 3 times. Okay, it's a fair coin. Now you know that these are all possible outcomes we have. Now what I said is I made one more abstraction. I said I'm not concerned about what actually happened. So what I'm concerned about is I defined x as a variable. X it takes variable values. So there I'm saying is this x is equal to number of heads. Maybe number of heads. I'll write it like this: number of heads. So now you know that this value can be either 0, it can be 1, it can be 2, it can be 3. Everybody agrees on this. This x can take value of 0, 1, 2 and 3. So what I can do is, now I will have to have a mapping. I'll have to have a mapping from the sample space. This is our whole sample space. So I'll have mapping from sample space to these numbers. Here if you see this number of heads, so here this will get mapped to 3. This will get mapped to 2. Okay, again this will get mapped to 1. This over here will get mapped to 1. This to 1. This over here to 1. Correct me if I'm wrong somewhere. This will also get mapped to 1. So this will get mapped to 0. Okay, so now you saw that we defined a mapping over here. We defined a mapping from the sample space to these numbers. Okay, to these numbers that a random variable can take. Okay, this is how we mathematics. I don't want to get into mathematical definitions of what a random variable. I just want you to understand the intuition behind that. Why are we doing it? Now you had an experiment, you performed an experiment. Okay, you got some output. Now you are not concerned about what the output was, but what you are concerned about is some other quantity. As in this case, we are concerned what is the number of heads there. Now you also have to assign probability to these numbers. Okay, so by natural question is how to assign this. As you know that each of these events we are considering is a fair coin, so each of them will have 1/8 probability, 1/8. So all of these will be having 1/8 probability. So what is the probability that x will take value 0? Now you know that there is only one possibility. This is the possibility where the number of heads is equal to 0. So this will have 1/8 probability. Probability that x will take value 1. So how many possibilities are there? I think 3 possibilities are there. For 2 also there are 3 possible. That's why I was telling you to correct me if I am wrong somewhere. So what will happen is, so this is 2. I think there should be multiple 2s. This is 3 heads, 2 heads. This is again 2 heads. This is 1. This is 2. This is 1 head, and 0. So if you see this 2 and this, so there the probability is 3/8, because 3 of these equally likely outcomes that were in the sample space mapped to this x is equal to 1. What is the probability that x is equal to 2? Again 3/8 if you see it. And then what's the probability that x is equal to 3? That's 1/8. Okay, now you see that these probabilities, again, why I call them probabilities? Now they again sum up to 1. If you just add them, add these things up, they'll again sum up to 1. Okay, now all of these are disjoint. So if you say x is equal to 0, x is equal to 1, x is equal to x is equal to 3, they are disjoint events. So okay, so if I make it in set form, so it will be like this. So there will be head, there will be 16 points, somewhat 16 points. Okay, and let's suppose these numbers, how many? 8 points. Oh, sorry, not 16. So there will be 8 points. Let's just make 8 points. If I just show it in the Venn diagram, so there will be 8 points, somewhat like this. Okay, then this outcome is mapped to 1, that is number of heads is equal to 1, and maybe this 1 is mapped to 0, and then these 3, let's suppose, are mapped to 2 and 3. Okay, you now see that all of these are disjoint, they have nothing in common. So if they have nothing in common, you can again use the union property. That's why this probability also follows the 3 axioms of probability. The first thing is the probability should be non-zero and less than 1, and it is following that. The second axiom was that sum of these probabilities should be equal to 1. So if they are here, you can see that sum is, if you just summation them up, this is equal to 1. Okay, and then what, and these are disjoint also, that's why you can perform the union, and the probability is non-zero, that you can clearly see. All the 3 axioms are sort of followed here, so that's why we also named as a probability. I hope that you got some clarity on what a random variable is. Okay, is it clear what a random variable is?
Yes, sir.
Show me the raise of hands. Nice. Let's take another example now. The example I'll tell you, and then you'll have to give me the probability. Let's suppose you have some basket or some urn is there, in which we had 20 balls. We have 20 balls, and each of the ball is numbered. So the ball is numbered like this. We have a ball is numbered as 1, second ball numbered as 2, 3, 4, till we have 20 balls, and they are numbered as 20, till 20. Okay, if you just pick up one ball, okay, you'll get a number from 1, 2, 3, 4, 7. You can get any number. You can get any number till 20. So what my question is now, the question I'm concerned with is, I'll pick up 3 balls from it without replacement. I'll not replace the balls. I'll just pick up these 3 balls and randomly select them without replacement. Okay, if I do the without replacement, then among these 3 balls, they'll have a largest number. You agree on this? Like, let's suppose I took balls 4, 5, and 8. Now you see that this 8 is the largest among them. I can take balls 1, 4, and 6. This 6 is largest number. I can pick up the balls like 2, 13, 12. This 13 is the largest ball among them. So one of the three balls will have the largest number. So now my question is that if we bet that the least the one balls are like the question being like this. So I think you understood the setting. You have three balls that you are randomly selecting from the urn without replacement. Okay, and the balls are numbered from 1 to 20. Now the question is, if we bet that at least one of the ball that we drawn has the number as large as 17. Okay, so what I want to do is, so I am drawing these three balls. So if I have to bet, let's suppose to win the bet, so at least the balls that I'm taking, the highest ball, the number of on the highest ball should be greater or equal to 17. Okay, and then what's the probability that I'll win the bet? What's the probability winning of the bet? I think you understood what do we bet on. We are betting on that when I take these three balls, so one of the balls will get the highest number. So what is the probability of that highest number being greater or equal to 17? Either it should be 17 or it should be way more than 17. So that we have to compute. So the first thing, how do we solve such questions, or how do you even mathematically model such questions? The first thing is we can introduce a random variable. What you can do, I'll say, let's suppose we'll take a random variable x. We'll denote x is a random variable. So this means let x denote the largest number selected. So this is largest number selected. This is a random variable. So now you know that this random variable, it can take values. What values can it take? It can take values 3, 4, 5 and so on till 20. Why can it take values from 3? Why not 1, 2? Because you are taking three balls. So obviously if you take 1 and 2, if you take like the worst scenario possible is you took all the least 3 numbered balls, that's 1, 2 and 3. Okay, and at least you will get this largest number will be 3 among the balls. You understood this point? How many of you understood this point? Why is the number from 3 to 20? It is not from 1 to 20. Because you are taking the three balls out of that urn, out of that basket. Now if you, even in the worst scenario case, you take this 1, 2 and 3, still the highest number will be 3. You cannot go beyond, you cannot go less than this. The first thing in the mathematics what I did is, so I had a problem with me. The problem was, what's the probability of winning the bet? When do I win the bet? I win the bet if I take these balls out and the highest number that I got on these balls, it should be greater or equal to 17. Now I say that, okay, I am defining a random variable. So let's suppose x is a random variable which is the largest number selected. Okay, but this large number selected will be based on the balls I'll take. Now I am taking three balls out of this, so this can take values 3, 4 till 20. Everybody with me? So how I can write it now? Now I can say, what is the probability that x takes I value? So let me find this first. If I find this, then I can see what is the probability that x takes values 17, 18, 19, 20, and then I can add them up. Okay, what is the probability that x takes I value? Let's suppose x takes value of 3. Okay, what is the probability of that? So I'll write it like this. So I minus 1 choose 2 divided by 20 choose 3. How many of you understood this? Otherwise I'll explain it. And if you agree on this, the probability that this random variable, the random variable basically means x, the largest number selected is ith number. So I am saying this is I minus 1 choose 2 divided by 20 choose 3. So this you understand. This you obviously is when you select 3 balls out of 20. This is total possibilities. So when you choose 3 balls out of 20, so this is the total number of possibilities that the value can take. And now why is this so? This is because, let's suppose you have now 3 choices. Okay, for the first choice you are choosing ith number. So what is the choice? 1 choose 1, because there is only one ball that has that number on that. So this is 1 choose 1. And then for the other 2 choices you have, so then you have the next 2, you have to choose next 2 balls. So now the remaining is that from this you have to choose from I minus 1 balls. Now you will choose those 2 balls, like which has, because numbers now can take value I minus 1. Let me explain it on the separate page. So now I know that x is equal to I basically means the highest number should be 1. So what is the value that it can take is, it can take from 1 till I minus 1. In order to like win the bet, my number should be, let's suppose I am talking about 17. Okay, so out of 3 balls, if one has 17, other 2 balls should have numbers less than 17. It should be 1, 2 till 16. That's what I'm writing over here. So when I'm saying that, what is the probability of x is equal to I? So I'm saying that out of these 3 balls, 1 ball got I. That this ball got I, and I means this is the highest number. Now these 2 balls have choices. The choice is that these 2 balls should have numbers less than I. Okay, how many possibilities are there for these 2 balls is, that means I minus 1 possibilities, because 1 to I minus 1. That's why I wrote this I minus 1 choose 2, because now from those I minus 2 1 choices I have to select 2 balls. Okay, so that's why this number appeared here. This is our favorable outcomes, and this is the total number of outcomes. How many of you understood this now, why I wrote it like this? Okay, the difficult part is not to solve the problem. The difficult part is how to mathematically model the problem, and then how do you comprehend this. So maybe in the initial go, when you are just looking at it, it might seem a little bit difficult. But once you sort of internalize it, once you think it through, it becomes easy. So again, I'll write probability of x is equal to I. First, I told you mathematics is like poetry. You have to understand it. Poetry, equations, these things are just a succinct format of what I have to convey to you. I write it in them in some short form. So probability x is equal to 1. So what's the meaning of this? Let me first explain the meaning. Now I have the context set for you guys. You know the problem about solving. We said this x basically says this is the number. If you go back over here, what I have made it. This is the largest number selected. I'll use the same name. So this is largest number selected. Okay, so if I now have to read it, if I have to read it in English, so this means what's the probability that the largest number selected is I. So this is what I mean. So among these balls, if you have to sort of imagine it, so we are taking 3 balls, so the highest numbered ball should be I. So now these 2 balls can take numbers 1 to I minus 1. So I said what's the total of favorable outcomes? So that I told is I minus 1 choose 2. Why? Because I have to select these 3 balls. Now I am selecting them in 2 ways. I am selecting the first ball, which is numbered I. So only one ball is there. I am saying 1 choose 1. And then for the second 2 balls, I have I minus 1 possibilities. I am choosing 2 balls from the I minus 1. That's why I am writing I minus 1 choose 2. What's the total number of possibilities of choosing these 3 balls? It is 20 choose 3. 20 choose 3. Okay, this is the probability that my largest number selected will be I. Now the question was, I have to basically compute probability of winning the bet. This is what I have to compute. I have to compute probability of winning the bet. So what is the winning the bet? Winning the bet means probability that the value x, this x should take value greater or equal to 17. Now if you see, there are 4 cases over here. It can be 17, it can be 18, it can be 19, and it can be 20. So these 4 cases I'll have to evaluate probabilities for. And for I have created a generic formula for I. Probability of x is equal to I is this. So I'll just put the values for 17, 18, 19, 20 into this formula, and I'll get the answers. So I think for 17, this probability is 0.150. For this is 0.134. These are approximate values. So for this is 0.119, 0.105. Now what will do? Probability of winning. Now you know that all of these are disjoint, so you can just add them up. Plus this, you can add all of these. So on adding, what you will get? You will get 0.508. This is the probability that you will win. How many of you understood this? How many of you understood how do we use these random variables? Okay, just going a little bit back. So what I did is, so sometimes we are not concerned about what is the actual outcome, but we are concerned about something else. Okay, so something is happening. So as we were in this problem, if you again fit into that realm, the problem here was actually I want to win a bet. I'm not concerned what will happen. If 17 comes, 18 comes, 19 comes, 20 comes, I don't care. But my problem was to win a bet. When will I win the bet? I'll win the bet if my outcome was 17, 18, 19, and 20. I'll win that. Now I have to model it. I said, okay, if I have to model it, let me bring a random variable. I'll say random variable means the largest value that I can get, the largest ball that I'll get, basically. So after that, when I created the random variable, I said, what's the probability that I'll get probability of ith number. So for that, I create a formula. And then now I know that there are 4 cases, 17, 18, 19, 20. I calculate probability for that, sum them up. Okay, in a similar fashion you can do with the problems where you're not concerned with the output, but you're concerned with something else, and that's why we motivate this problem. So what we try to do is, and we take the whole sample space. If you again see this where we took this, so we took the whole sample space, we mapped them onto this. Okay, so that's why this random variable basically is sometimes called as a function. If you see it like mathematics, they'll say it's a function from sample space to these numbers. You assign the numbers to them. Okay, so this like the function, it will take this input. Let's say it will take head. Okay, it will give some real output. It give output 3. Okay, this is a function, so it takes some input, gives some output. So that's what sometimes if you see these random variables, they'll see it's a function from sample space to some real numbers. Okay, so and then there are different types of random variables, which we will also discuss about what discrete random variables are, what these continuous random variables are. Okay, so now what is a discrete random variable? It's just an introduction, and then probably we'll dig deeper into this. So what is a discrete random variable? Now you understood what random variable is. So random variable is basically it's a mapping which takes this whole sample space and it maps it onto numbers. Okay, so what is this discrete random variable? Discrete random variable basically is which takes discrete values, or it takes countable values, countably finite values I'll call, or maybe like a set of classes. So let's suppose I have this number of heads. So you know that number of heads can take values 0, 1, 2 and 3. So here you only have 4 values to take. So but there are some values, let's suppose, where it can take countably infinite uncountable values even. So what is that? Let's suppose you are watching a time on your clock. So you now know that this can be, if your clock is of infinite precision, it can take infinite values. Okay, so if I take, let's suppose this x is equal time on the clock, time on the clock. If your clock is of infinite precision, so you can write it like this. This is 10, 20, and then you will write something on milliseconds. And if infinite precision, then you know that infinite, this is a continuous value. Time is basically a continuous quantity. So this over here is a continuous random variable. So what's a discrete random variable? Well, it can take discrete values, or even height of people. Let's suppose if the height of people, if we do not, the height can be between, let's suppose, 0 to some 3 meters. So now you know that any value can be taken in between. So this again is a continuous random variable. So if I say, let's suppose x is equal height of people, now you know that this can be continuous. Okay, there are infinite values which this random variable can take. So we call this as continuous random variable. Continuous random variables. And we have discrete random variable. What discrete is? Discrete basically takes a set of fixed values, okay, which you can count basically. So now what's the discrete value? That's why it's called discrete. Takes discrete values. So example of discrete values could be x is equal number of heads. Okay, or x is equal, let's suppose, age in years. Age in years. Maybe let's suppose age in years for humans I'm talking about. So age can be from 0 to, so maximum we can take 200. I don't know if somebody has crossed 200 like in present era, but you know that now it can take discrete value. It can take 0 year, 1 year, 2 year, 3 year, something like that. We'll just consider discrete values. We won't consider half a year or something like that. So now you know that this is a discrete random variable. So discrete random variable, in short, they take discrete values and from a set of discrete value. And second thing is we have this continuous random variables. Okay, continuous random variables take continuous value. So I can write it like this: types of random variables. So we have two types: discrete random variable and continuous random variable. Okay, so these are the two important things. And now we'll define what is a probability mass function, probability density function, and then cumulative distribution function, that we'll see. But first, are you clear with this? Are you clear with what a random variable is and what are the types of random variable and what are these two types of random variables? Okay, if you are clear, let's do some other problems so that you do it yourself, and then sort of we'll see have you understood the thing. Let's suppose I'll take a problem. The problem goes like this. So independent trial, we are flipping coins. So independent trials consist of flipping a coin, and flipping a coin has p probability of coming heads. Okay, there is p probability the heads will appear. Okay, so we are continuously flipping the head. We are continuously flipping the coin. So until a head appears, we do not stop. Okay, we do not stop until a head appears. So my question is now, what I say, I'll introduce a random variable. I'll say x is equal to number of flips. Okay, so what I am doing is I am continuously making n flips. N flips. That's how we'll restrict one more thing. So I'm making n flips. I'm continuously doing a trial. I'm tossing a coin. So in these n flips, I'll stop if a head appears. So it can be like this. First I saw tail, I'll see head. I'll stop. Okay. So how many flips did it take to reach a head? 3 flips. Okay. Now I can be like this. Tail, head. Okay. Now you saw that 5 flips. It took 5 flips to reach the first head. So I'll stop it here. So now what this random variable is number of flips. Number of flips till the first head is seen or till the first head appears. So now you give me different problems. Now what is the value that you can take? X. First tell me how many values can it take. Is it a discrete random variable or is it a continuous random variable? What do you say? Is this x a discrete or random variable? Is this a discrete or continuous random variable? What is it?
Discrete.
Yes, discrete. So Zakir, can you explain why is it discrete?
Yes, sir.
Can you explain why this x is discrete? Discrete random variable.
Sir, it may be discrete or continuous, but because it depends upon the flip. If the head comes, then it will stop. Otherwise, it will last so long.
No, no, I said like there are n flips. So n
Okay,
flips
sir.
means it'll be a discrete number again. So let's suppose it can be like this. So how I can tell you this? So let's suppose n flips will have some number. N flips will be some thousand or something. Because anyways n will have to be have a number. So if it is even, let's suppose 10,000. If it is still if
Then,
it is
sir,
10,000, if it is 100,000, whatever it is, but still it will be a number. So now still it will be
that,
countable.
that sir, it's a countable entity, so it will be a discrete.
Discrete, yes. So if you make n flips, the n flips is basically countable. So that's why I want to bring this example up, because here you will get a clear distinction between what a discrete random variable is, what a continuous random variable is. So let's suppose I have number. How many numbers are between 0 and 1? So this is basically uncountable. You cannot count it. This is like there are two types of infinity. One is called as countable infinity, and second is uncountable infinity. So here you can see you cannot count this. So what you might have even read about countability also, where you can set the mapping between these between entities and the real numbers. Sorry, and natural numbers. So here if you see that these flips, anyways, if I have to stop, let's suppose if they were 100,000 even, still I can count them. Still it's a discrete set. Okay, it is not going continuously, but here if you see that this is going continuous, it won't take discrete values. It can take value 0.01 and the value can be 0.001. It will be sort of continuous values it can take. So here the question was we introduced a random variable x was number of flips, number of possible flips till first head appear, So what are the number of possible values now? It can take values 1, it can take values 2, because on the first flip head appeared, and it can take values till n. This is what the values can. This is what the values of the random variable is. So it will be from this set. So now it can be like this. It can be head. It can be tail head. It can be tail head. It can be tail and head. Okay. So now you will have to have a mapping of this. So this will be mapped to this. So this over will be mapped to this two flips. And similarly, last will be mapped to this. We're having a mapping. So now if I tell you what's the probability that x is equal to 1, because now you know that this value can be probability x is equal to 1. Now you'll map this problem back. This is basically equal to probability probability of head. Okay, this is equal to p, because you know that I told you upfront in the example that the probability of head is p. So what is the probability that x is equal to 2? So this is basically probability of first we'll have tail, then we have head, and you know that these two events are independent. This is probability of tail multiplied by probability of head. Okay, so this basically is what is the probability of tail? Anybody? Probably what is the probability of tail?
1 minus p.
This is 1 minus p, and this is p. Okay, and similarly if I say what is the probability of this x is equal to n, so what will it be? This is probability that everything will be tail and last flip will be basically head. So in that we'll have 1 minus p raised to power n minus 1 multiplied by p. Everything everybody okay with this? Okay, and this is how you compute these things. Again, you can check. So if you take a union of all these, now if you take union of probability of x is equal to 1, probability of x is equal to 2, you'll take union of these. You'll again see that this will sum up to 1. Okay, I hope that you got some intuition and some clarity on what a random variable is. Okay, now we'll see in these discrete setting if we have discrete random variable, if we have this discrete random variable. We define what's called a probability mass function. Okay, we divide this probability mass function. We define this. So what is the probability mass function? So first see, let's first see what this mass is basically. So let's suppose now x can take value 0, 1, 2, 3. Okay, in terms of, we'll again revisit the example where we started with this, where x took the 4 values. So this was the example. So number of heads we had, because in the flips we flipped the coin, and in that we had x is equal to number of heads, and it took these number of these. And in the Venn diagram setting I told you this is like this. So you have 1, 2, 3, 4, 5, 6, 7 and 8 possibilities. So one of them got mapped to one head, one of them got mapped to 0 head, and these got mapped to 2 heads, and this got mapped to, let's suppose, 3 heads. Okay, this is what values we can take. Now what I want to see is, I want to see where is the mass sort of concentrating. Okay, we have this line. We can take value 0, we can take value 1, we can take value 2, and we can take value 3. Consider like this. See this probability as a bag. See this probability as let's suppose 1 kg of material. Let's suppose. See this probability as 1 kg material. Now you know that this material is to be divided between these 4 entities. Okay, because you know that sum of all these events, it again comes up to 1 because it follows probability. It follows the axiom of probability. So if you say probability of this is something, probability of this, probability of this, if you add all of these, the probability will be equal to 1. Now consider that 1 is equal to some mass. It is equal to some 1 kg of material. And now what I want to see is if I have to distribute this 1 kg among these 4 possibilities. So which of the possibilities will get how much amount? That's why it's called mass function. You want to see the concentration. So now you know that this got 1 by 8. So here if you see it, this will get some mass. Let's suppose 1 by 8, something like this. So if you see this one, I think for 0 and 1, it is 1 by 8 and 1 by 8. For these two, it's I think 3 by 8. So 3 by 8 means this much. So I got something like this. Okay. So now you see that now I have to distribute this 1 kg of mass onto these 4 possibilities. Now if you see that this is it's a distribution of this total 1 onto this. So this is what actually the intuition of what gist of this probability mass function is. So we want to see the concentration, where this mass is concentrated. Okay. So this is probability mass function. So if you see now this, so I'll just make it in the diagram which you will probably see in the books. So you can see it like this. So there they'll write possible outcome of this. X can take value 0, it can take value 1, it can take value 2, it can take value 3. Okay. So for this, the value of probability is 1 by 8. This is 1 by 8. For this again 1 by 8. For this is 3 by 8. And for this again 3 by 8. And you will see functions like this. So again, this probability mass function again is a function. What it takes this as input and gives the output some probability. Okay. Or maybe if you see it in the histogram setting, so in that setting you will see it gives you these towers. This is why it's called a probability mass function, because we want to see where is this mass concentrated. So if I have to distribute this 1 onto these possible outputs, this is called, I'm talking about discrete random variable. Okay, on this discrete random variable, I have to see, because there are set of possible outcomes and I want to see where this 1 is concentrated. And then you can sort of figure out, and this will lead us to the distributions. Okay, the first thing I want you to see is that where this mass is concentrated. And sometimes we can have mass like this. Let's suppose we have, these are possible outcomes of these are the possible values that a random variable can take. You can see outcomes like this like this. Okay, but whole of this will sum up to 1, and this is what is called as probability mass function. It is basically the function. Okay, why is it called a mass function? Why is it called a probability mass? Because probability mass, we want to see where is the concentration of these values. What is a function? And function is basically a mapping. So function will take an input of these values and it will assign a probability to that input. That's why it's called a probability mass function. What is the random variable? Again, the mathematical setting, it's again a function, but it takes input from the sample space. Okay, then give you some number. Okay, here if you see what is the probability mass function, it's another function. So what it does is it will take these outputs. So whatever the values that a random variable takes, it will take them and give them a probability score or probability number it will give them, and it will basically distribute the mass over them, because the total probability mass is 1 and we have to distribute it among different values that we have in the discrete setting. In the continuous setting, we'll have some continuous mass distribution that we'll see there. But I hope that you have this probability mass function is clear to you for these discrete random variables. Is it okay? Everybody clear on these points?
Yes, sir.
So if you're clear, like let me again show you some more examples of this probability mass function. So I think I had some examples with me. Again, the same thing. If you have, let's suppose we have these A, B, C, D, maybe some events. Let's suppose A, B, C, D. A, B, C, D are 4 events that a random variable can take. Okay, this random variable can take this. Now you know that. Let's suppose this is the sample space. Sorry, not the random variable. Random variable can take outcomes. Let's suppose 5, 3, and say 4 or something like this. 5, 3, and 4. So what I'm saying is, I'll say this A and B, this maps to 5. Now this is a generic setting. Initially we took a problem, number of heads. So there we had 8 possible outcomes were possible, and then we had 4 numbers 0, 1, 2, 3, and we mapped them. Now I'm taking generic problem. Let's suppose this is my sample space. It consists of elements A, B, C, and D. And let's suppose I'll make one more assumption, then all of these are equally likely. So the 1 by 4 is the probability of each of these singular events, each of these singleton elements in here. So after this, if you see, this A, B got mapped to 5. Let's suppose this C got mapped to 4 and this D got mapped to this 3. and this over here is my random variable x, what my random variable x can take. Okay, so this basically tells me, so now I have to give a function probability. A function should be there which will give some value of probability to this, because I have distributed this 1 over this 5, 3 and 4. Now you know that this 5 will get basically this a and b. Now you know that it's 1 by 4 plus 1 by 4. This 5 will get number of 1 by 2. Okay, so how do we write it? So we write it like this: probability of x given this x. So this is a probability mass function. So sometimes you can write it also like this: probability, this x takes value this x, what is the probability of that? Okay, so or you can write it like this: probability. So we can write in set format, this is probability of this, we call it w, it belongs to the sample space, these elements basically, such that x is a random variable, x of w is equal to x, this is small x basically. This we can write it like this. So any notation is basically equivalent. So for this x is equal to 5, so if I write probability, this x value takes equal to 5. So what is this equal to? So this will be equal to 1 by 2. This is what is called as probability mass function. I think we also discussed it, but that time we did not named it. Okay, so when we are sort of assigning the probability, so the probability number of heads is this much, so that again was probability mass function. Okay, so this over here we discussed that. So this basically is probability mass function. Okay, before even naming it, we saw it how to compute these probabilities. Okay, in order to get a nice view of what this probability mass function again does, so I'll like to show you some graphs probably. So the graphs will be there, so I'll maybe in the next session we'll discuss about the graph, so as to get more understanding of these and what this is for, because these things will lead us to distributions, and then from the distributions we'll have different types of distributions. Now the agenda for next class will be to first know what are different types of these random variables, like Bernoulli random variable is there, binomial random variable is there, uniform random variable, then we have geometric random variable. There are a lot of random variables. Okay, and from that we'll try to go to distributions, what distributions are, and what before that we'll probably learn about what expectations mean. Okay, once we are at the distribution, then we can know what Gaussian distribution is, what is a Poisson distribution, and different distributions. And that distribution probably will Gaussian distribution, I have planned to use that in logistic regression, and other distribution like binomial distribution we'll see. And this distribution has like very smooth properties. Okay, and based on that discussion we can move towards that logistic regression part. Okay, I hope this is clear. So here in today's lecture, in summary, what I can say is we introduce what are random variables, and then from the random variables we introduce concepts regarding the random variables, what can they do and why are they required, and we saw some different problems how to formulate them into the random variable function. I hope this was clear, and if it is not clear, please watch this recording once again. And now I'll stop the recording. If you have any questions, please feel free to ask.